Okay, can you hear me now? Okay, sorry. Now we get some results with batch normalization. And after that, after we implement all these models with additional layers, we will see how our metrics will change, and we can select the best model. Also, we can repeat the same with layer normalization. Here is the image about layer normalization with comparison of batch normalization. The difference is only that we compute the statistics on other dimension. That is one difference. And all algorithm about layer normalization, about inference and training stage will be the same as for batch normalization. Also, define model and define our trainer and train this model. After that, compute metrics. And that's, I think, first part of the special layers about batch normalization and layer normalization. Also, if you have any question about normalization, you can ask now. Okay, let's moving to the dropout layer. I think it's quite a simple layer because here we just turn off some neurons of our model with some probability, and we generate a mask with only ones and zeros from the Bernoulli distribution with this probability, and we just turn off some neurons of in the layer. Also, it's important to remember that dropout is needed for prevent overfitting, and may be always useful for classification task. However, here we use regression task, and it was shown that dropout sometimes not help to prevent overfitting and decrease results for regression task. You can see here figure with different dropout rates with different values of metrics, and for 8 regression dataset, and you can see that here dropout dramatically decrease our results. However, here we use California housing dataset, and you can see that with small dropout rate we can slightly increase results. And also it's important to remember that always is used only 0.1 dropout rate. We not will use more values. Yes, yes.
Just as you can see from the picture, for example, for the diabetes data, the R-square statistic doesn't kind of reduce with the dropout rate. Can you please tell probably what can be associated with, because it's kind of, it is important probably for which data sets the dropout rate doesn't help to kind of reduce overfitting, or if it's actually accessible.
Yes, for regression task, it most of the time it decreases results, because when we use dropout, after applying dropout layer, we need to scale our value to the value proportional to 1 divided by 1 minus p. As a result, we have the same mean value. However, variance of these values is may be changed. So that's why for regression task, it may decrease results. However, for classification task, I think you can always use dropout after some linear layers, and it will help to prevent overfitting if we find some optimal parameters for tuning model and also for dropout rate.
So that means they send through to classification level.
This picture is about a regression task. Yes, and here we can also repeat this code and use dropout layer and define some probability to be dropped. And after that, one more time train model and see results. Already we can see that our validation loss are decreases in relation to other model, but after that, after we train all model, we can see difference with RMCA metrics. And then combine all layers to make a final model. Here we will use dropout layer, and also we will use batch normalization, because we can always combine these layers in some order. First of all, apply linear layer, then activate batch normalization. It may be batch normalization or layer normalization, then ReLU or some other activation, and then dropout. Also train model and evaluate. And now we can see difference between these metrics. Yes. I forget about this compute metric function. Here we can repeat all this very fast. Okay, and as a final result, we can see that here our final model must work better. However, also with our dicts. Okay, and then as a final result, we can see that our final model perform better than all other models and perform better than our raw model. However, we can see also that the main important part of our modification is using dropout, because dropout helps in these tasks, helps to prevent overfittings. And also we can see that our RMCA on the test part of the dataset is much better than values from the previous seminar. It also means that our final model is better than raw model. And I think that's all about special layers. And also, if you have any question about special layers, we can discuss it. Okay, then moving to initialization, and as we will see, is a very important part of training process, of optimization process, because for some initialization techniques, our model will not tuned or optimized as well as for modern initialization techniques. First of all, implement initialization function. Here we implement a function which receive initialization function from torch. Here we just apply weights from linear layer to our initialization function, and also for bias values. If our initialization function will be only with zeros or ones, we can also initialize our bias with ones. In other cases, we can initialize bias values with some constant. Then since we want to fast modify our initialization techniques and also our model, I suggest to implement all train pipeline in one function. And also we want to see how loss will change from the initial state. And for that aim, we implement get_eval_loss function. First of all, start with constant utilization techniques and with zero initialization. Okay, also I think you can suggest what will happen if we initialize our model with zeros, and maybe someone may say what will happen. Okay, what happens if we initialize our model with zeros? All zeros? Maybe you have any suggestions?
I'm not sure that something related to gradients will be seen, so their velocity will be reduction.
Yes, it's the case when our initialization is a constant initialization. However, here we use zero initialization, and since we use ReLU activation after applying linear layer and activation, our output of a model will be zero. Then when we compute gradients, we also will use in these gradients our output value, and since output value is zero, our all gradients will be zero. Then as a result, we can see that our model will not change. It will be always the same results. Results are slightly changing because our output layer will compute gradients in relation to our loss value, which is not zero. However, all previous layers will be zeros. After that, as we already say, that we can use constant initialization. In this case, it's initialization with all ones, and our model will be very bad. However, it can be optimized, but not as with other initialization techniques. We can see that we start with a very bad loss and also metrics. Then moving to the random initialization, here we need to remember that if we initialize values with very large values, it leads to exploding gradients problem. However, if we initialize with very small values, it leads to vanishing gradients, and all our gradients will be close to zero. From the theory, we also can understand that it must work better than with constant initialization with zeros or ones. Here, first of all, we apply the normal distribution. We can see that it starts with not so big values as with constant initialization. However, it optimizes very slow. I think we need more than 10 times higher number of iteration for optimize this model. And also we can optimize using uniform distribution and initialize our weights from uniform distribution from zero to ones. It will be slightly better than normal distribution because here we truncate our values with zero and ones, and our gradients will not exploding. However, it's also not optimal choice for initialization. We see that we start also with very big loss values and big metric. However, it may be optimized for some optimum solution. And also we moving to modern initialization techniques. First of all, start with Javier normal distribution. This initialization technique was developed especially for sigmoid activation, for hyperbolic tangents activation, because when it was developed, people not use ReLU and other modification of this activation. And also we can use a function from torch, just call the same, but with Javier. And here we have value which computed. This value means an input features. This value means output features in our linear layer. And gain, it's just scaling factor which computes depending on our activation. And we can see that it's much better from the starting value than all other activation. I have here 40,000 of RMC, while for other activation, only after 5 epochs we have these values. And in the same way, we can apply not only Javier normal distribution, but also can use Javier uniform distribution with the same value. However, it's bound for minus A and plus A. And also we get some good results for this activation. However, this activation often used only for sigmoid or hyperbolic tangents. This initialization used for this for sigmoid activation. However, in our model, we use ReLU activation, and it was theoretically proven that for ReLU, it's better to use K-Ming distribution for initialization of the weights in the linear layer. Here we also can see how we can compute our variance. It's just the same gain. It's a scaling factor, which depends only on our activation, our linear layer, and number of input feature. And in the same way, we can use storage function to initialize. Initializations. Yes. And one more time, we can apply these values for uniform distribution and use gaming uniform for initialization. And let's look for the all results with different initialization and how it perform in comparison with all other. Here I start with second epoch because on the first we have very big values and we will not able to see what happens after that epoch. And we can see that with zero initialization, our model not changing as supposed. For initialization with all ones, it slightly changes, but it's very bad in relation to other modern initialization techniques. With normal initialization, we also start with very big values. It happens because with normal initialization, sometimes we initialize with very big values, which leads to exploding gradients. Then we can see that our Teaming and Javier initialization works much better on starting with the first iteration. And as results, we also can see that two variants of Teaming initialization works better in the first iteration and in the last iteration too. So it means that we need to also remember what activation function we use. And for this activation function, we need to use proper initialization techniques. So I think that's all for today's seminar. If you have any question about initialization techniques or about special layers, we can discuss it. Okay.
Я вот небольшой такой вопрос. Ну, я на лекциях просто когда был, немного пропустил, наверное, или просто не показали. Есть ли какая-то литература по курсу? Ну, то есть, чтобы отдельно читать? Ну, кроме статей.
Что еще раз к курсу?
Литература, ну, какая-то именно вот...
Я понял. Ну, я думаю, что пока ничего такого не выкладывали, но, в принципе, я могу посмотреть и выложить что-нибудь, что может быть полезно.
Ну, просто на GitHub, если загрузить, это будет очень классно. Спасибо большое.
Ну, хорошо. Мы посмотрим тогда, что можно сделать. Okay, that's all. I think we can be free now.
Okay, thank you. Bye.
Можете еще раз объяснить, в чем разница между крайним non-distribution и крайним uniform distribution? Кроме того факта, что uniform distribution лучше делает. То есть в чем разница?
Ну, сам коэффициент мы считаем точно так же. То есть это какой-то скейлинг-фактор, и нам нужно на такой корень. Ну, здесь, кстати, еще, да, здесь корень из 3 мы должны домножить. Ну и потом просто в случае равномерного распределения мы просто минус А плюс, а в случае нормального распределения мы просто используем в качестве variance это значение. Это количество, это, да, на вход, фичей на вход. Для Хавьера тут у нас еще fan-out, это на выход. Да, для каждого слоя это оно будет по-разному инициализировать. В общем, с самого начала здесь у нас функция, которая по каждому слою идет и инициализирует.
Вот обычно вроде как больше нормы используют одновременно с дропаутом. Прям ставили рядом.
Ну, вот в нашем случае как раз-таки batch-норм с дропаутом лучше всего работает для нашей задачи. Ну, в принципе, оно может и по отдельности использоваться. Ну, просто, как правило, есть какой-то линейный слой, активация, batch-норм, дропаут. То есть вот эти 4 слоя, они могут просто как бы вместе стекаться, и все. Но, в принципе, и можно... Если, например, у нас какая-то большая модель, есть в конце отдельно какой-то просто линейный слой, 2 линейных слоя на выход, там уже, как правило, batch-норма нету, там просто уже линейный слой, активация, дропаут, линейный слой, и все. Какой-то энкодер, а потом, где уже будет batch-норма, дропаут, а в конце только уже дропаут.